Hi friends, today I am giving a lecture on optimal binary search tree. So optimal binary search tree is one of the application of dynamic programming. So the optimal binary search tree is we are constructing possible number of binary search trees. Among them, which binary tree has minimum cost, that tree can be treated as optimal binary search tree. For a given set of identifiers, we have to construct the all possible number of binary search trees. Among them, which binary search tree has optimal cost, that binary search tree can be treated as optimal binary search tree, that is OBST. So before going to OBST, first what is a binary search tree? So binary search tree is a binary tree in which each and every node contains two children. One is left child and another one is right child. Now, what is the condition we have to follow in binary search tree? So each and every node in the left subtree are the less than the value at the root node. Each and every node in the right subtree has a value. That value is greater than the node at the root node. So that means in binary search tree, we are storing the identifiers. So all the identifiers at the left subtree are less than the identifier at the root node. All the identifiers at the right subtree are the greater than the identifier at the root node. So for example, so that is one at the root node, the identifier is if. So we can take the identifier do. It is less than the identifier at the root node. So because, so in if first letter is I, so in do the first letter is D. D is compared with I, so D is less than I. So the identifier do is present at the left hand side of the root node. Now we can take another identifier, that is Y. So in Y, the letter W, first letter is W. W is compared with the first letter of if, that is I. I is compared with W. W is greater than I. So the identifier Y is present at the right hand side of the root node. So this is a binary search tree. In that binary search tree, all the identifiers are stored. All the identifiers at the left subtree are less than the identifier at the root node. All the identifiers at the right subtree is greater than the identifier at the root node. Next, suppose we want to search a identifier X. We want to search a identifier X. So first, this identifier X is compared with the root node. If it matches, the search is successful. If it does not match, okay, then this identifier is compared with the root node. Suppose if X is equal to, so that is fur. Okay, fur. So the identifier is fur. So the identifier fur is compared with if. So the letter F and the letter I. At the root node is if, the first letter is I. Here the identifier fur, the first letter is F. F is compared with I. So F is less than if. So the search continues at the left subtree. Next, go to do. So in do, the first letter is D. In fur, the first letter is F. D is compared with F. So F is greater than D, then search goes to right side. Right side is empty. There is no identifier is there. So then the search terminates at the right hand side of do. So then we can say that the search is unsuccessful search. Suppose X is equal to the identifier do. First, in the identifier do, first letter is D. D is compared with I. D is compared with I. D is less than I. So then the search continues at the left hand side. So then left hand side the identifier do is there. D is compared with D. So it matches. So then we can say that search is successful search. So in this way, the binary search tree is a binary tree in which the identifiers are stored. All the identifiers at the left hand side is less than the identifier at the root node. All the identifiers in the right subtree is greater than the identifier at the root node. Suppose we want to search a particular identifier that is present in the binary search tree or not. First, this identifier is compared with the root node. If it is greater than the identifier at the root node, then the search continues at the right subtree. If the identifier is less than the identifier at the root node, then the search continues at the left subtree. So in this way, we want to search a particular identifier in the binary search tree. If the identifier is available in the binary search tree, then the search is called as successful search. That if the identifier is not present in the binary search tree, then the search is called as unsuccessful search. Next, so suppose let us assume that the set of identifiers A1, A2, A3, AN. So there are n identifiers are there. So what is the condition you have follow? A1 less than A2 less than A3 less than AN. So here suppose the identifiers are do, if, int, while. There are four identifiers are there. The first identifier is do, the second identifier is if, the third identifier is int, fourth identifier is while. Here what is the condition we have to follow? A1 less than A2 less than A3 less than A4. So we can compare the first letter. D is compared with I. So D is less than I. Next, I is compared with I. So the first letter matches, then go for second letter. F is compared with N. F is less than N. Next, I is compared with W. So I is less than W. So compulsory this condition should be satisfied. Suppose we are given a set of identifiers A1, A2, A3, AN. The condition is A1 less than A2 less than A3 less than up to AN. Let P of I be the probability of successful search for an identifier. So P of I always represents the successful search probability. So by this probability we can search an identifier in the binary search tree. If the identifier is present in the binary search tree, then we can say that is successful search probability. P of I always represents the probability of successful search of an identifier. So that is AI is nothing but identifier, that is 1 less than or equal to I less than or equal to N. So successful search probabilities always starts with 1 and ends with N. Next, unsuccessful search probability. Suppose we want to search an identifier in the binary search tree. If that identifier is not available in the binary search tree, then we can say that is unsuccessful search probability. Unsuccessful search probability is denoted as Q of I. So Q of I is the probability of unsuccessful search for an identifier. Unsuccessful search probability is always starts with 0 and ends with n. 0 less than I less than or equal to n. Successful search probability always starts with 1 less than or equal to I less than or equal to n. Next, so to obtain the cost function, we have to insert the imaginary node or external node in the binary search tree. Suppose we want to find out the cost of the binary search tree. While evaluating the cost of the binary search tree, we have to insert imaginary node or external node in the binary search tree at the leaf node. So how many number of internal nodes are there? How many number of external nodes are there? So internal nodes can be represented as circles and external nodes is represented as square boxes. So external nodes are represented as square boxes, internal node represented as circles. So the successful search always terminates at the internal node. The unsuccessful search always terminates at the external node. Okay, the successful search always terminates at the internal node. The unsuccessful search always terminates at the external node. This is external node and this is internal node. So internal nodes are represented as circles and external nodes are represented as square boxes. So how many number of internal nodes are there? N number of internal nodes are there. How many number of external nodes are there? That is n plus 1 number of external nodes, where n is the number of nodes. N is the number of nodes in the binary search tree. The total number of external nodes in the binary search tree is n plus 1. The total number of internal nodes in the binary search tree is n. So successful search always terminates at internal node, that is circle. Unsuccessful search always terminates at external node, that is square boxes. Next, the successful search always terminates at internal node. So what is the probability of successful search for an identifier is P of I. Where the successful search terminates? The successful search terminates at an internal node. That internal node is at a level L. Okay. So then what is the probability? So that is nothing but P of I into level of A of I. So P of I is nothing but probability of successful search for an identifier A of I. Where the successful search terminates? At which node the successful search terminates? The successful search terminates at an internal node. So what is the level of that internal node? That is level of A of I. So multiplying with this probability and where the identifier is at a level. At which level the identifier is there. So multiplying these two, P of I into level of A of I, this is the expected cost contribution for the internal node. Next, what is the cost contribution for the external node? External node is nothing but unsuccessful search for an identifier. That is, failure to search for an identifier in the binary search tree. So what is the probability? So that probability is unsuccessful probability, that can be denoted as Q of I, where the unsuccessful terminates. The unsuccessful search terminates at an external node. So what is the level of that external node? So that is, unsuccessful search always starts with 0. So then what is the level of the external node? Minus 1. That value is multiplied with Q of I. So Q of I is nothing but unsuccessful search for an identifier for an identified external node E of I, that is Q of I into level of E of I minus 1. What is the meaning of minus 1 here? Unsuccessful search always terminates with, unsuccessful search always starts with 0 to n, but successful search always starts with 1. So because of this one, we are removing minus, we are subtracting minus 1. Level of E of I minus 1 is multiplied with the unsuccessful search probability. So then what is the cost of the binary search tree? So the cost of the binary search tree is equal to successful search cost plus is multiplied with unsuccessful search cost. Sorry, this is plus successful search cost plus unsuccessful search cost. Successful search cost is sum of the successful search for an identifier. So sigma pi into level of A of I plus unsuccessful search sum of unsuccessful search for an identifier, that is sigma q of I into level of T of minus 1. So this is the formula for finding out the cost of a binary search tree. So this is for successful. So and this is for unsuccessful. So sum of successful plus unsuccessful is equal to cost of the binary search tree. Then we can go for example.